Okay, let's start. So welcome everyone to this first session of last day of CHES. So we'll have a session on white box crypto with 3 talks. And the first talk will be about revisiting computational analysis against internal encodings in white box implementations. This is joint work by Yufeng Tang, Zheng Gong, Bin Li, Lianju Zhao, and Zheng will be giving the talk.
Okay, thanks for the introduction. And I'm Zheng Gong, and I'm very happy to give the presentation about our work on the white box implementations, especially on the internal encodings. And the outline of our presentation will be 4 parts. And first, we will give a quick description on the white box cryptography and the internal encodings. And then we will revisit the proposed computation analysis on the white box crypto, especially white box block ciphers. And then we will give a introduction on our new computation analysis method, which is named the algebraic degree computation analysis ADCA against internal encodings. And then finally, we will give a conclusion. And the first, white box attacker context is quite strong assumption, because in the black box, traditionally crypto analysis technique, they assume the attacker can only access the input and output. And we know the things are changed in the attack model. So in the gray box, in the side channel context, we assume attacker can have power and a fault injection, something like that. We call it side channel to enhance their attackability. But in the white box model, we assume the attacker can do everything he wants. So we assume the attacker have full access to the implementation, extracting the secret key from the memory, and even use the reverse engineering. So that's the definition of white box. So in such a restrictive model, so our goal is still to preventing the cryptographic algorithm from key extraction in such a model. So in the past 20 years, we have 3 main framework about the white box cryptography encoding. The first is CHES, which is proposed by Cho et al. 2002, and it's applying linear and nonlinear encodings, make the AES and DES become a net list implementation to avoid the key extraction. So in the 2020, Rania and Prunier proposed the self-equivalence, which is a new encoding framework, and it applying a fine self-equivalence. We can see the S-box of AES is a fine function, because you have a 8-bit permutation and you have a fine function applied to this permutation. So they use a fine self-equivalence. They put a fine self-equivalence permutation instead of the original one. So you can have a S-box which have different affine function, but the same permutation as the original S-box. So you can apply different encoding to that. And after that, they use this technique combined with the implicit function to make ARX block cipher can be white box implemented. So this is the framework we have nowadays. And in this talk, we were focusing on the first framework, CHES, which is the oldest one. And for the encoding network, we were applying input and output encodings, which is we have the T table, and then I is the input encoding and O is the output encoding. And we have 2 different encodings, which are named in external encoding and internal encoding. For the external encoding, we will change the input and output of the original cipher. For example, for ES, you have the text vectors. If you add the external encodings, you will get the different text vectors compared to the original one. But for the internal encoding, they are pairwise invertible. So you will combine all these internal pairwise encodings, you will get rid of it. And the cipher will just act as the original one. So these two kind of encoding. So for the white box crypto, if you add external encoding, it will be secure, more secure than without it. But for the internal encodings, we have many attacks on this part, and our position is also on this part. So internal encodings in CHES framework have a new definition in the CHES 2021, which is given by Khaled et al. And they define this internal encoding as DIBO, diffused input and blocked output, which means 8-bit input and 32-bit output. So this is the name. And for this diffusion, they will use 4 or 8-bit nonlinear permutation to hear the output combined with a linear encoding. So they have a blocked output. And attacks on white box implementations can be divided in 2 categories. First is structural attack. This attack uses some algebraic technique and require the full details and the reverse engineering to the implementation. So it's more complicated, and they need the people to do some human efforts to have the successful attack. But for the automatic attack, we can use power and fault analysis, those side channel analysis tools, and it's more convenient and it's more automatic. So we are focusing on this part. And then we revisiting the computational analysis. Actually, for this computational analysis, we mean differential computational analysis. It's similar to the power analysis. Here is the trace of power. And because the hardware have some errors or something like that, you will get the trace like this. But in software, it will have no errors or the noises. So you can get a very clean choice. Yes. And similar to the power analysis, if you have the correct key guess, you will get a pick. And so the attacker is easier than the power analysis, because you can get as many choices as you want. It's from the software. If you do the hardware experiment, you need to repeat the experiment from IC or a chip. So it may be some restrictions on that. And published computational analysis doesn't explain why all these internal encodings are failed. They give some reasons, and the different analysis method give different reasons. So we revisit what they have concluded right now. For example, in the very beginning, the FSC 16, they said the failure of internal encoding is is because the watch transform can distinguish the correct key. And after that, in the ACS 18, they said the Hamming weight of linear encoding caused the key leakage. And in CHES 19, they said the target function caused the key leakage. And this paper at HPE Access 2020, Lee et al. Said that the imbalance of linear encoding caused the key leakage. So you can see we have many proposed attacks, and each attacks have a new idea about how the internal encoding failed. And recently, CHES 2021, Khaled said that the invertibility of linear encoding caused the key leakage. And, they propose we should use 8-bit nonlinear encoding to avoid the failure. So this is the proposed analysis method, and this is the countermeasures they proposed, and you can see they have different reasons. But all these countermeasures lack of the analysis of properties of nonlinear encodings, and the lack of the comparison of the compatibility and the time complexity about all this analysis, which is better and which can be more generic or automatic, less of this analysis. So that's why we give our revisit on this and give our new analysis method. And we give a refined structure from DIBO. We just took the 8-bit to 8-bit path instead of 8 to 32. So we have this function here, and the linear and the nonlinear encoding combined together. We call it a F function. It's active like a random mapping. Right? And after that, we choose input for a key guess. This because the S box is no for a cipher, and we guess a key, and the computer is inverse. So we have 8-bit input and output. And if the key guess is right, the key, K is equals to key star, then we will get the internal encoding. This are concealed with each other. But if we guess the wrong key, this will act like a random mapping. So that's our theory basis of our analysis. And if we know the S box degree, for example, the AES S box degree is 7. So if it is internal encoding, then we have the F functions degree. If it's random mapping, this degree will equal to the S box degree. So it's almost the 7. So we have those maybe have these differences, so we can do a comparison. So finally, we can distinguish the correct key. So the theory is quite simple. And then we do the experiment. We have 3 combinations. Use the linear and the nonlinear. Which kind of encodings we use? We have these 3 combinations. The strongest one is this one. So this 1 or 2 is already broken in the proposed method. So you can see if the key guess is right, we almost have 8 ANF functions, which degree will equal 7. And if we guess the wrong key, then we will have 0 function have the degree 7. Because we randomly choose the internal encoding, and this is the percentage. So you can see this definitely distinguishable. The behavior is totally different, and this is also the same. And for the non-invertible linear encoding combined with 8-bit level nonlinear encoding, so we still distinguishable from the distribution. And we combine the probability together. We have overwhelming probability to distinguish the correct key, because this is the failure probability. It's very, very low. We can distinguish. And for the strongest internal encoding, we use invertible linear encoding and 8-bit nonlinear encoding with degree 7. Now we can hardly distinguish with each other. The percentage is really close to each other. And the percentage is 3. So actually, this answered a question about the proposed paper, because in the papers they said use this combination is a countermeasure. Actually, the attacker still have the non-negligible probability to be successful. So, but in the practical experiment, this percentage you need to pile up with, this is only 1 S box. So many you do the experiment or you failed, but it's not means your countermeasure is successful, because this probability is some kind of low. So if you try more times, you will eventually successful. This encoding is still not strong enough to resist all the attacks. And we finally generate our tool to the ADCA analysis. We based on the algebraic degrees, which we observed from our experiment. So the procedure of ADCA is really simple. we use 3 steps of ADCA. First, we collecting those computation traces, and then we make it as a equation matrix, and then we solve this matrix to compute the degree, and then we compile the maximal numbers of degree from this equation matrix, and to find if it is distinguishable. So to solve this equation linear system, we can use Gaussian elimination method pre-computed. We don't need online compute, so it's very fast. And for the degree D internal encodings, we computed the number of Boolean functions with degree D. So we add them up. So for example, look, if we want to defeat in 4-bit nonlinear encoding, we set D equals 3. And if we want to beat the 8-bit internal encoding, we will set D to 6, because D to 7 is equal to the Xbox degree, so you can hardly distinguish it. So the time complexity we listed here is from the degree 1 to degree 7, and you can see it's nearly the same, because we only need to pre-compute the equation matrix with this time complexity. And the online attack is just about the degree and the size of the key. So for here, we only guess 8-bit key, so it's really small. And for all the proposed methods, we have a comparison about the time complexity. So ADCA has the lowest complexity, and it is an automatic tool to analyze. So we set the degree to 6. So all the degree under 6, we can have the successful attack. We can see the result here. For the degree 7, the attacker is failed. Because the successful percentage is really low. So we repeat it, I think 1,000 times. So we cannot get the result. It's similar to the proposed work. But I think if we increase the experimental times, we can get some successful cases, and we show it in the paper. Maybe in 1,000 experiments, we can success 2 or 3 cases. Yeah. This is the experimental setup. We have 14 cases of combined encodings. And also for the random mapping, we have 7 degrees. So compare together, we can see the 3 cases of computation analysis are good. First is SA. It can break all the cases. And the ISA is the second, and ADCA is next. Their capability are the same, these 3 kind of computational analysis methods. And the compare with SA, it lacks of encoding analysis. So it can hardly be automatic because it's fully algebraic analysis. So and we also reveal the weakness of algebraic degree. So compared to the ISA, it's a structural attacks focused on the invariability of linear encoding. So it lacks of analysis of linear encoding. So now it's the conclusion. The vulnerability against the computational analysis is related to the degree of encodings. That's our observation. And hope it answers all the problems in the past papers. Each coordinate function of the encoding with degree 7 is a countermeasure, but we would like to say it is a mitigation. It only conceals something in the white box implementation, but it can actually protect the key. ADCA has a general computation analysis tool with the lowest complexity, and we upload the code in the GitHub, so it's welcome to have your comments or the ideas about how to improve this analysis later. And for the future work, we are suggested by the many researchers and the reviewers. They said, how can computational analysis to defeat the external encoding? Because with internal encoding, it works, but at the external encoding, DCA is powerless. So there's some published work combined with DFA and 8-bit external encoding. But this work actually is not statistical analysis anymore. It's more like an algebraic analysis. It's used DFA in the algebraic analysis. So how to combine with DCA is still a problem. That's all. Thanks for your attention.
Thanks for the talk. So we have time for questions. So first morning after the banquet. Yeah, I have one question. So do you think your technique would be robust against countermeasures like shuffling or desynchronization, these kind of things?
No, this is computation analysis only focusing on the traditional internal encoding. If you use masking and shuffling, you need to change to the high order DCA.
Okay, yeah.
Use high order DCA, you can have the positive results. But for the ADCA, it only works on the traditional countermeasures.
Yeah, you need to have clean samples of the output of the...
If you have masking, you have shuffling, you need to have the high order DCA to deal with those countermeasures.
Yeah. Thank you. Yes.
Thank you for your talk. I have a small question. How do you estimate how do you compute the algebraic degree? Because you mentioned some equations and I didn't.
Yes, because for example, for all these encodings are not the size is 8-bit, so the highest degree is 7. So you can change this 8-bit permutation to ANF equations, and then you can calculate the degree. It's used we said here. You use Gaussian elimination to calculate the degree of the ANF functions.
Okay, thank you.
We have another question here.
This is just a clarification. You're saying that the attack is automated,
yeah.
But as far as I understand, you still need to pinpoint the output of the S-box so that...
Excuse me?
You say that ADCI is an automated attack.
Yeah.
But as far as I understand, you still need to pinpoint to isolate the output of the S-box to be able to... Okay. So which means that there's a manual... there's some amount of manual effort.
Yeah. Okay. I understand what you ask. Yes. The only thing we need is to get the input and the output of white box implementation, and this cannot be automatic. The engineer should do this, and after that, for this case, because we can from degree 1 to degree 6, we can automatically run the analysis. So that's why we say it is a generic tool. For other computational analysis, it can only focus on a certain degree. It cannot change to different degrees. And this work is not find this input and output is not so hard, because in software you can put the breakpoint in the input and the output. You just get that. Yes, for the reverse engineering work, it might be time costly, but in the theory, we think it's doable.
Okay, thank you.
Any last question? Okay, if no, let's thank the speaker again. Okay, so the next talk will be about probable white box security in the strong incompressibility model. This is a joint work by Estuardo Alpinez Bock, Chris Brusca, and Russell Lay. And Estuardo will be giving the talk.
Thank you. Thanks, Matthieu. Yeah, hi everyone. Thanks for being here. And welcome to my talk on. So my talk is gonna be, yes. So I'm gonna continue on the topic of white box crypto, and I think we got a nice introduction already. So yeah, just to recap, we're considering an adversary with complete access to an implementation with an embedded secret key. And we also assume that the adversary can control the execution environment. So we want to keep implementations secure, even given such adversaries. And this talk will be related to the property of incompressibility for, for white box ciphers or for white box encryption schemes. And so incompressibility is about taking a scheme of conventional size and then via a compiler, I transform or I obtain a functional equivalent scheme of a much larger size. And yeah, the idea is that they are functional equivalent. And then this large one should give me some security properties that I will be discussing now next. So yeah, so I'm gonna talk a little bit about this topic now. And yeah, so why this property is important is because so in the previous talk we saw an attack that extracts the key from white box programs, but in practice white box programs also are under threat of redistribution attacks or code lifting attacks, which take place when an adversary, instead of trying to extract the key, he simply makes a copy of the program, because the software program, and then redistributes it. And so if the copy it's exactly the same, the program is going to give me the functionality that I need. So I don't really need to spend time trying to extract the key, and I can then just copy. So we need to have some. So the white box programs need to implement some protection against such attacks. And so in the white box related literature, there's been different mitigation techniques proposed and then formally defined. And so amongst them is incompressibility, which we'll be talking about. Then there's traceability, which is when I watermark the program. And then if I find an illegal copy, the watermark lets me know who this program originally belonged to. So we're considering like some kind of malicious user or traitor in this sense. And then there's also hardware binding, where the program is meant to run on exactly one piece of hardware and cannot run anywhere else. And software binding, when the program is meant to be merged with some other software program. So let's talk about incompressibility. So it was introduced in 2013 by Delerable, Lepont, Palais, and Rivain. So thank you. Yeah, and so the idea is what I said in the beginning of the talk, that we start from an encryption scheme of conventional size, and then we obtain a functional equivalent one that's much larger. And so we call it incompressibility because the program should only remain functional on its entire form. So if I remove some fragments of it, or if I try to compress it, it should lose its functionality. And then, of course, given this large program, I shouldn't be able to determine what's the key of the original scheme, the short key. So because this talk is about security notions on incompressibility, then we need to go a bit through the syntax of incompressible white box schemes. So we depart from a scheme of conventional size with an encryption and decryption algorithms, and a key generation algorithm that generates a key of normal size. So you can think of 128 bits, and then we have a white box compiler. And so the white box compiler generates this white box incompressible program based on this secret key. And then this program should achieve this correctness property. So anything I encrypt with the white box program should be decryptable with this shorter key. And then we also want that this white box incompressible program is much larger than the encryption program. So one nice thing about this property is that if I am using the encryption in an environment where where white box adversaries are a threat, then I can use this this large program, this incompressible program. But if on the decryption side we don't have that threat, then I can use the shorter keys, and the other way around. So yeah, yeah, that's quite nice. And so the security, as it was originally defined in the first paper, we consider an adversary that gets that white box program, that large program, and then we give access to the adversary to a decryption oracle. So with that white box program, he can encrypt messages, but then we also give access to a decryption, and then the adversary also gets access to a recompilation oracle, they call. So the recompilation oracle simply generates new versions of the same white box program, but yeah, based on different randomness. And so eventually, after the adversary has been playing around and reverse engineering and so on, he generates a program P, and now we're going to check whether this program, whether we can encrypt messages correctly with this program, and we're also going to check whether it's substantially smaller than the white box program. So of course, in the definition, we have some more formalities, like we specify a bit more which fraction of messages should be encryptable correctly. So it should be a large fraction, but maybe not necessarily everything. And then how much smaller the compressed program should be to consider the adversary successful. And so in a later work, Fuchs, Karpman, Kirchner, and Minot introduced the strong incompressibility model, and what they wanted to capture some more security properties than what I previously discussed. And this corresponds essentially to INCPA under leakage. So the way it's defined here, now we consider two adversaries. So first we have an adversary that gets the white box program, and then from that white box program, the adversary derives some leakage and then gives that leakage to the next adversary. And so this is going to be the one that's going to be playing the INCPA game. We check, so the leakage is bounded. It cannot be like everything, of course. And then given the leakage, the adversary plays an indistinguishability game. So yeah, you give two messages, and then one of them is encrypted, is randomly chosen and encrypted, and then the adversary tries to guess which message it was. And yeah, and then he tries to guess here. And another particularity of this model is that the adversary gets access to an encryption oracle, so he can get he can get queries of for encryption. Yeah, and it's important. Oh, sorry, it's important to keep in mind that these two adversaries they don't share state, right? The only thing they share is this leakage. Yeah, and so if you're familiar with these security models, like you can see that this one is indeed stronger. It captures more security properties, because here we know, for instance, that the encryption scheme should not reveal anything about the message that is being encrypted. For instance, whereas in the previous one we didn't necessarily have that. So the previous one was a bit more about not being able to predict the outputs of the program. Yeah, so this one was indeed stronger. And so, yeah, one thing to consider is that there's another work by Belare, Kane, and Rogoway called big key symmetric encryption, and they consider the exact same model, basically. And big key symmetric encryption is a little bit different from white box incompressibility, but they consider the exact same model. So basically INCPA under leakage. So now I will talk about some idea, like basically what I will be telling now is kind of the story of this paper, how we came to like what happened here. Because we started with some idea, we wanted to prove something in the strong incompressibility model, and it didn't work, and that led us to an impossibility result. And so yeah, we had we thought that we can build an encryption scheme securing the strong incompressibility model, and we wanted to build it solely based on standard assumptions, so on one-way functions or one-way permutations. And this idea was going to be derived from another work we did previously. This is a screenshot from another presentation I did some years ago where we presented this construction, and this construction was an incompressible scheme in the simpler model, not in the strong model. And so here, maybe some of you are familiar with this construction. Is a GGM tree. These are all PRGs, and then on the top I have a seed, and then I iterate this PRG on the outputs of a previous PRG, and this gives me a PR. Via this construction, I can get a PRF. So in the bottom we have the outputs, the PRF outputs. The secret key of the PRF is the key at the top, and then the input is the path. Like the input bit string tells me the path that I should follow to the corresponding output. And so in this construction, what we did was we had our original scheme was PRF where we just use this key at the top, and then we iterated the PRG to obtain the output. That was the original one, and then the white box one with the large key was some layer in the middle with pre-computed values. So here in the third layer, you see this large key K. And yeah, the nice thing is that you can see that whether I have a PRF with the key, this key with this big key with this large layer, it's the same as if I have a PRF with a short key in the top. So both give me the same, can give me the same outputs. And yeah, in that construction, we use this for generating MAC values. And so we thought that we can simply plug it in a, sorry. We can simply plug it in for masking messages, and then we would achieve INCPA security. Or we could just use that construction for generating keys and then plugging them in some conventional encryption scheme. And then that would give us INCPA security. And it kind of makes sense maybe if you think about it. Like, I mean, I don't know, I thought it was a nice idea. But then we run into some problem. And the issue was that, for instance, if we, when we wanted to prove security, if we consider that we give the adversary some leakage, let's say that the leakage is just a block from that large key, and then the adversary has this leakage, but then since the adversary had access to an encryption oracle, the adversary could query it many times, and then based on the queries he was receiving, he could start obtaining or deriving more information from the key. So in the end, the amount of leakage he had was larger than we initially allowed. And so by the time the adversary is playing the INCPA game, we don't have we cannot make any arguments, any information theoretic arguments on the amount of information that the adversary doesn't know with respect to the large key. So yeah, so we didn't really know, we didn't know how to prove this. And then we found a paper from Daniel Vix from 2013, where he explained difficulties when trying to prove security in the standard model for leakage resilient schemes. And so he had a meta reduction framework where he showed an impossibility result. And then we apply this impossibility result in the context of the strong incompressibility model. And so the impossibility result, what it did was build a pair of adversaries who do not share the state, like those adversaries that were considered in the model I showed before. And they were inefficient. And then based on input-output queries to the encryption oracle, they would determine the key, and they would break the INCPA security. And then there was a simulation which was efficient, and with two adversaries that were sharing state, and that way they would be cheating to break security. But in the eyes of the reduction, the simulation and the inefficient adversaries were indistinguishable. And then we use this as an impossibility result. And so there's kind of a catch to this impossibility result, and it's that it works if the scheme that we're considering is key fixing. And so what's key fixing? a key fixing scheme is a scheme that lets you determine the value of the secret key based on inputs and outputs, like based on a set of inputs and outputs. And you can think of it as given an input, an output, and a key, it's difficult to find a different key that gives me the same input-output mapping. That's a way of thinking about this property. And if the scheme we're considering has this property, then this impossibility result applies. And there's ways of getting around this, like there's ways of constructing schemes which do not have this property explicitly. And we know a work from Haze et al., where they build a non-key fixing scheme, but it's a nice result, but it's a bit far from what we would want in real life, given that it uses a very, very large key with a lot of fractions that are never used, never accessed. And yeah, I wish I could explain it better, but I think, yeah. So yeah, I'm just gonna leave it like that. And yeah, this is what I was saying. And in the paper, we also analyzed AES in CBC mode and determined that for AES, if we model the CBC as a truly random permutation, that we can also say that it's a key fixing scheme. And so our conclusion is that we cannot really expect to have incompressibility in the standard model, or strong incompressibility in the standard model from a scheme such as AES. Yeah, and with this, I finish my talk, and thank you for your attention.
Thank you, Estuardo. So we have plenty of time for questions. Yes, Lucas? The mic is coming.
Okay, so I understand that it doesn't apply to AES. To which schemes it might apply? Could you speculate?
So there's different ways of proving security in that model, and one way is using a random oracle, and another way is using some different assumptions such as universal computational extractors, which are not so accepted as other assumptions. And another way is to construct a scheme the way I was describing, like very artificially having a very large key with a lot of fractions that are never accessed. And so for real life schemes, I wouldn't know for which ones. Yeah, and so for AES, it seems like it's not possible, but I wouldn't know for which ones.
Thank you.
Other questions? So just to be sure to understand, so previous constructions in this model were proven in the random oracle model.
Actually, so in the paper from Fook et al., they had some constructions, and there were no arguments on there were no arguments on the encryption oracle. So in other words, there was a gap there. And then this paper was edited, and they added a random oracle, so such that they could prove security there.
All right.
Yeah.
Okay. 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 So if there is no other question, let's thank Estuardo again.
Thank you.
Thank you. Okay, so the last talk of the session will be given by Alexei Udovenko about crypt analysis of ARX-based white box implementation. This is a joint work with Alex Biryukov and Baptiste Lambert.
Thank you for the introduction. Hello, everyone. So today I'll be talking about crypt analysis of RX-based white box implementation from crypto last year. So let's start with the introduction. We've already heard about white box cryptography, and I will focus on the case where we talk about the hardness of extracting the secret key from the implementation. So the user or the adversary has full access to the implementation, but it should be hard to extract the secret key. And the most challenging direction in this setting is to implement existing primitives, which is normally done with the AES block cipher. But today we have a very special design, which is the spec block cipher. And I want to mention that this direction is very challenging. We couldn't make any designs that stand against the attacks for the last 20 years. And today we will be breaking another such design. So I will try to gradually introduce the design ideas about this white box implementation, which is due to Ranea, van der Smith, and Purnell from Crypto last year. And the first idea is so-called implicit computations, where normally when we try to compute some function, f of x, we write down the output parts, the polynomials, or some computational circuit to compute them. While the idea of the designers is to consider so-called implicit functions, which are simply polynomials that relate the input and the output of the function, and not necessarily say how to compute it, while we still want to compute it, so that the authors require that these functions are linear in the output, meaning that we can plug in any input for x, and we get a linear system of equations for the output, which we solve and compute the output. So it gives us a quite convoluted way of computing a function, but it's useful for white box purposes that gives more freedom for designers. And the designers applied it to the RX ciphers, meaning that we work with modulo addition modulo power of 2. It's normal addition of registers in the CPUs. And if you try to implement it directly, to write down the polynomials, for example, you can notice that the degree, the algebraic degree is very high. So the most significant output bit has degree n-1. And if you compose it with linear encodings, with random linear maps, as we usually do in the white box setting, it will be too large to store in the implementation. On the other hand, there is a bilinear implicit function that describes the modulo addition, which has degree 2. So we cannot write down the polynomials for the addition, but we can write polynomials that describe the addition. And in addition, why it is useful is that we can also compose our function with input and output encodings, which we often do in the white box setting. And in particular, we can use any low degree input encoding and linear output encoding. It has to be linear because we want to preserve this property that allows us to compute using implicit functions. And finally, the designers suggest to obfuscate these implicit polynomials by graph automorphisms, but I will not talk about this here. And the final ingredient of their design are the so-called self-equivalences of modulo addition. So it turns out there exist a large set of maps, affine maps A and quadratic maps Q, such that if you compose them with the addition, you get nothing. You get again the modulo addition, right? So these two structures define the same functions. And this allows to add some variability to design to make it harder to attack by adversary. And as the target, they chose the block cipher spec, which was designed by NSA and has simple RX structure. It has modulo addition here, and the rest are just linear maps like rotations, XORs, or XORs with the key. And it has different block sizes and key sizes. So now I will talk the high-level structure of the design that we will try to attack. In the black rectangles, you see essentially an obfuscated round function that, according to the designers, should behave as a black box oracle, so that from its representation, we should not learn about its internal structure or anything. So it should be like a black box Oracle. And looking a bit forward, I will say that we don't break this assumption. We use it as a black box Oracle, but we can still break the construction. So what is inside of this round function are the usual affine encodings, which are just random maps used to obfuscate the function. So they are generated in such a way that they cancel out when you consecutively compute all the round functions, but they don't cancel out inside these boxes. The second component are the self-equivalences that I mentioned before. So if E is the encryption which contains the model addition, we have A affine self-equivalence and Q is quadratic self-equivalence. And this is one of the key ideas of the designers, to split these self-equivalences and so that they don't cancel immediately, because if Q would be inside this box, it would just cancel and we will assume that it's not there. But because it's separated, it's not canceled, and we have a quadratic encoding of this round. So essentially, altogether, these 5 functions, they're equivalent to one encryption round function. But because they are split across 2 obfuscated rounds, they don't cancel. So they only cancel when you try to compute this sequentially one by one. And another thing, you can mention that we cannot go infinitely with these encodings, and particularly in the input, we have to stop, and we cannot use random encoding. We can only use some affine self-equivalence. And the same thing in the end, we can only use a quadratic self-equivalence, no random encoding. So this is the setting without external encodings, where we really want to have an implementation that performs an actual encryption of the cipher, so the spec cipher in this case. But since in the white box case, we don't succeed a lot with designs, we often allow ourselves to use random external encodings. So we could use some random maps here and here that preserves the strengths compared to intermediate rounds. And this is the main setting considered by the designers, and we will also attack this setting. So I will now try to summarize all the attacks that we have in the paper. First, we showed that in the setting without external encodings, we can mount a standard algebraic attack, because if we have linear encoding, we can do linear algebraic attack. If we have quadratic, we can do quadratic algebraic attack. And it had to be adapted to the RX setting, which wasn't done before, but it can be done with small technicalities. And here by target A, I mean a finely encoded round, and by target Q, I mean round with quadratic affine encodings. Then we proposed a technique called round Oracle optimization, where the idea is that the implicit function could be obfuscated by the designers, but since we have a black box Oracle, we could just interpolate an implicit function in the lowest degree terms, which means that obfuscating by higher degree maps is not really useful. So we can always obtain lowest degree implicit functions. And for the quadratic case, this costs a bit more. This we didn't implement on practice, but this should also just work. The next attack is based on the fact that the implicit function for the model addition is bilinear, which means it's linear in input and in output at the same time. So we can use the same idea that used to compute the function to compute its inverse. Right? We plug in the output, we get linear system on the input, and we can solve the linear system and get the input. So we can invert rounds, compute them in the reverse direction. So this covers the affine case. And in the quadratic case, it can be done only partially and requires some additional brute force. And the main attack that we propose is the round decomposition. Given black box access as the designers require to the round functions. We can decompose them into components, and this essentially breaks the implementation. And finally, when we can decompose multiple rounds, we can recover subkeys that are used between them and then combine them to get the master key. And we implemented all of these attacks in practice, except this one. And so we applied them to 32-bit and 64-bit version of spec, the white box designs of spec. So I will now describe how to decompose model addition wrapped with affine encodings. So assume that we have a black box access to a function like this, where we have unknown maps C and C prime, which we want to learn. The first step is to notice that the right branch is just the identity, so it's linear, and we can find in the output space the image of this branch because it's linear, and then move things out to have right branch that just goes in clear. There is slight difference because the least significant bit of modular addition is linear. So we'll get n+1 linear bits that go like this, and n-1 bits on the left. And then we also have the first carry bit that we also have to take into account. So after this step, we have this structure where we don't know this affine maps B and A. And also the carry, which is affinely equivalent to the actual carry bit. The next step is to triangularize this maps B on the left side, which means if we look at the matrix representation, we recover half of the coefficients so that the new matrices are just lower triangular. And to do this, we consider differences. So we encrypt some differences using the structure, because we can put some difference in the left input, in the right input, and get the difference in the output. And we use the property that differences don't propagate towards least significant bits. So in particular, if we look if you look at the differences in the output at the linear space that they span, if it has maximal rank, it means that the least significant bits in the input difference and in the output difference has to be equal to 1. So this gives us information about these maps and allows to get this triangular shape when we do it iteratively for each bit. The next step is to recover these triangular maps using differential probabilities. I'll just briefly mention that the idea is to distinguish two shapes of differences, two shapes of input differences, and we can distinguish them because they have different distributions. So if you look at distribution of output differences, we can distinguish them and learn bits of these unknown maps. So we end up with this structure, and where we don't know these maps A and the carry bit. And the idea is just to fix the right-hand side so that we get structure like this, where we XOR a constant, add a constant, XOR a constant, and these constants can be recovered in a bit-by-bit manner by solving, by finding solutions modulo 2, modulo 4, modulo 8, and so on. And it turns out there are always 8 solutions per such structure, and if we can choose any of these 8 solutions for different independent y's, so for different independent right-hand sides, and this gives us a valid candidate for all these maps A. And there is some problems with this carry bit, but this can be resolved. And once we have a candidate for these maps, we can essentially move these Feistel maps away towards the encodings, and also invert this map and recover the final equivalence of the carry bit, which I will mention later, so that we get this structure where we finally know this affine map C and C prime. So this is the original Oracle that we try to decompose. And now I will talk about the main attack, which targets the quadratic encoding. So to do this, we studied these self-equivalences, where on the right you have this affine quadratic self-equivalence, meaning that this structure is equivalent to just the addition. Which means that since in addition we have this identity branch, it means that at least half of the quadratic map should be linear. But in practice, we studied the quadratic equivalences generated by the implementation and observed that there are at most 3 independent quadratic outputs. So not even half, but just 3 different outputs. And each of them contains 1 or 2 quadratic monomials up to affine equivalence. Right, so they're extremely sparse. And as an example, you can see monomials of the shape x0, y0, or monomials that contain many linear terms, but again, they're just equivalent to monomials. And so we use this, we assume that this is always the case, and we use these properties to decompose the round functions. And here you can notice that this quadratic self-equivalence, it is moved to the next round. So in the actual round, when we try to decompose, it is given in the input side, not in the output side. So here Q I minus 1 is exactly this self-equivalence part. But we also have linear layer of spec that is there, and another linear self-equivalence. And what happens is that the linear layer of spec moves around these monomials of the self-equivalence Q, and we can observe them on the right branch of the function, which are moved directly to the output. So if we look at the output and find quadratic functions there, then essentially most of them will be exactly outputs of this function Q. So this can be done with some linear algebra. And then once we have these quadratic functions, we try to decompose them into monomials. So the problem we want to solve is to, given a function in the expanded form like this, to find representation where we group the terms and have small number of products, essentially 1 or 2 products in this case. And this can be done using so-called linear structures, which is a well-known technique from Boolean functions, which is essentially a probability 1 differential over our Boolean function, which corresponds to the linear terms. And if we take the dual space of the linear structures, it will give us the linear space of all these nonlinear terms. And then we can, because there are only 4 of them, we can just exhaustively find pairs that decompose the function into a small number of monomials. And then we can represent our quadratic affine encoding in the following way. Here, small q corresponds to these monomials that we recovered. So we know this small q. And q prime is essentially diffusion, affine diffusion that diffuses these monomials to the state, adds them to different places. And that's what we don't know. We don't know where this function adds them. And we also don't know these affine maps. But what we can do is to find inputs for which this quadratic function is 0, because we know this q. And then essentially there is no quadratic part at all. We have an affine encoded addition. Then we can interpolate the implicit function. And again, because it's bilinear, we can invert this part. But nice thing is that this inversion also works when we have input for which q is not 0. So it always works. And in this, as a result, we can remove the bottom part by always inverting it and obtain directly access to this part where we just can directly learn the affine diffusion operator. And once we get this quadratic map, we can invert it, which is in general difficult because inverting quadratic maps is difficult. But here it's extremely sparse, so you can even invert it by hand. Then we detach it from current round and attach it to the previous round because it belongs there and it gets canceled with the corresponding affine self-equivalence. And then we have rounds which are finally encoded, and we can run the attack from the first part of the talk. And finally, we can combine multiple consecutive rounds to recover the master key. And this concludes my talk. So for the implicit framework, what we've shown is that the high degree graph obfuscation is not really useful. We can always recover implicit functions by interpolation. But the general idea of using implicit functions is a very interesting tool and useful for white box designs because it allows to encode more functions than in the usual way, but it probably needs other target than just one round RX. And we also proposed algebraic attack for the RX designs. And we showed that one round with this affine or sparse quadratic encodings is just too weak in the black box setting. So there is no way to be useful for the white box setting. So at least we need either to pack more rounds inside this implicit function or to have stronger encodings. And please have a look at the paper. There are more results there, and the code is also available. Thank you.
Thank you. Any questions for Alexei? Yes, thank you.
Okay, thanks for your presentation. And I have a question. In before for the CGL framework, if we use 8-bit SBox, the algebra attack, the complexity is really low. And if you want to increase the complexity, you need to input many implementation costs. But from the implicit framework, the algebraic complexity increase very fast, although we can attack it by this method. So I feel there's something right we have done in this implicit framework, right? So you mentioned we need other targets. So do you have any idea what we can continue to do to improve the algebraic complexity of the attack? Because now it's 2 to the 64, right? It is the complexity.
No, all the attacks were polynomial, especially the algebraic attack is n to the 6.
Okay.
So if you have 64-bit, it will be 2 to the 36 for the quadratic case. So it's we implemented, it works.
Okay.
Yes. So yeah, as you say, it's a bit higher complexity than usual, but this is because the here they use quadratic encoding for the full state, which takes a lot of space.
Yes.
So the attack complexity is proportional. It's quadratic or cubic in what we store in the white box setting. So
yeah, the size is bigger. So if we change it to like modular addition to the multiplication, it will be better or nothing will change?
It could be better, but you need to find an implicit function that is linear in the output.
Yes.
And that's not often exists.
Yes.
So it exists, for example, for the inverse in the finite field, which is potential candidate, but it's more difficult to protect it.
Okay, thanks.
Any other questions? So maybe a follow-up question. So what actually the complexity of the implementation, the scheme in N?
The complexity in N is cubic at least.
Cubic, okay.
Because it always solves linear system of equations just to compute it.
Okay. So your attack is quadratic in the complexity of the system, of the scheme.
It depends which attack, but often queries to the Oracle are really dominating.
Because an idea would be to use a larger state, right? And maybe your attack could become.
Yeah, some of the attacks can, like for 64 bits, it took like 1 hour maybe for one round. So it's 64 bits is slow, 120. But the generation was also very, very slow. So maybe it took 1 day to generate them and then 1 hour to break one round.
Okay. Yeah. Other questions? Yes, Estrado?
And in the end, you mentioned that one could consider stronger encodings. And maybe I missed it, but what would be an example of a, or do you know what?
Yeah, that's a good question. So first of all, we used the sparseness, the extreme sparseness of this encoding to break them. So maybe find non-sparse encodings. But the problem is that in this setting, we cannot directly use any random encoding. The encodings are coming from the self-equivalences, and they are very restricted. So if we could use somehow random encoding, this would make it stronger.
And if they were not sparse, would that affect the performance of the cipher? Or is there a reason why they are sparse?
Yeah, the reason is because they come from the self-equivalence. Here. Yes. But the performance, yeah, it will not affect because they store essentially in a dense shape, so it will not affect the performance. But it will make the attack harder. It's just the question whether it's possible to implement like this.
Okay. Thanks.
Maybe one last question. It's time for caffeine then. Okay, so let's thank all the speakers of the session. So the next session on white box crypto will be at 10:45 in the same room. Thank you, everyone. Oui, j'ai partagé. Lorenzo, c'est d'accord. Je parlais avec Ademan et Damien. D'accord, ok. Et bon, je veux juste changer quelques mots avec vous, parce que je pense que je parle plus ou moins de la même chose. D'accord. En fait, j'ai vu les derniers papiers que vous avez